The UGC lecture series on computer science. Here we are having the subject that is theory of computation. Let me start with what we had seen as far as the previous episode is concerned. So, we have the multi-tape Turing machine, then followed by the language recognized by the multi-tape Turing machine. It differs from the single tape Turing machine in the sense that how many number of tapes are allowed to process any that is input. Since we are having multiple tapes, multiple heads will be there. So, simultaneously your Turing machine can read from different tapes with the help of different heads from different positions. And as far as the capability of the Turing machine is concerned, it is going to be the same as the class of language recognized by a single tape Turing machine. So, there is a need for transforming the given multi-tape Turing machine into its equivalent single tape Turing machine. So, those things we had seen as far as the previous lecture is concerned. Moreover, we have seen the definition and how a non-deterministic Turing machine is processing strings or processing the input. As far as this episode is concerned, here we are having the code for Turing machine. There is given a Turing machine normally in the transition form. So, how it will be transformed into the binary equivalent, that is in integer format, and then based on that we will be having the definition of diagonal language. And there is a proof for that is showing that the diagonal language is going to be a non-recursively enumerable language. These are the three things we are having as far as this episode is concerned. Let us start with that is what is need for the Turing machine code. So, normally a Turing machine is represented by some number of components. What is going to be the tape content, and what are the various transitions, what is the input alphabet, and what is the tape alphabet. So, these are the things available in the Turing machine definition. But when we want to represent a Turing machine in a Turing machine tape itself, so this complex form of representation will not be good for us. There is a need for loading a Turing machine in the Turing machine tape itself. So, if we find that the Turing machine is represented in the form of an integer or in the form of a single string in the binary form, then it will be very easy for processing the Turing machine which is loaded as input in a Turing machine tape. So, now the question is how will you transform the Turing machine which is in the descriptive form into the binary form, that is in the string. So, we need to have some common that is assumptions here. First thing is whether it is going to be tape alphabet or it is going to be the input alphabet. So, they are expected to start with the suffix that is 1. Maybe if we are saying the states, we wanted to have the states starting from q1 and then q2 etc. up to qn, that is going to be last state, and by default we assume the q1 is going to be the first state. And then regarding the symbols are concerned, the symbols are expected to start with that is say index 1 then going up to the last one. So, every symbol or state they are all going to be represented in the unary form. So, unary form in the sense for example, if I is the number which you want to represent, we will represent it in terms of I number of zeros. So, this is the way we are this mechanism we are using for transforming a Turing machine in the conventional form into the binary form. So, here we have the definition. So, given a transition, so we know that a Turing machine is given for us means there is a finite set of transitions given for us. So, if it is going to be transition, there is del of qi comma xi is giving you qk comma xl comma dm, and the meaning here is from the ith state for the jth symbol in the tape alphabet, the resulting that is configuration is we end up in the kth state in the set of all states, and this xj, I mean that is the jth symbol in the tape alphabet is replaced by the lth symbol from the tape alphabet, and finally what is the direction we have to move. We assume there are some number of directions available. So, here we say that it is going to be the mth direction from the list of directions given in the Turing machine. So, this is what the transition, and now the question is how this will be described in terms of some integer. So, we know that these I, j, k, l and m are all integer quantities, but not 0. So, now every integer there is I, j, k, l, m, they are all going to be represented in the unary form as follows. So, the integer I is denoted by writing I number of zeros, then j is returned by writing j number of zeros, and finally it is m is represented by using m number of zeros. So, there is a need for separating all these 5 components. So, we will use 1 as a separator for the individual components. So, 1, then followed by 0 power j 1, then 0 power k 1, then 0 power l followed by 1, and finally it is going to be 0 power m. So, when we read this particular that is transition, it looks like an integer, or it looks like a binary that is quantity in the string form. So, now a Turing machine is given for us means we will be having some number of transitions in the similar form. So, now we have to call that is each code, I mean there is each transition as a code Ci if it is going to be the ith transition. So, then if you are having n number of transitions like this, there will be n number of codes given for us C1 to Cn, and now the question is, when you want to form a single integer out of all these codes, how do you have the separation among the codes? Already we have used the symbol that is 1 as a separator for separating the individual components of a transition. Since we are having 5 number of components in each transition, we need to use a single one as a separator for separating the individual components. So, now as a separator of the various codes, I mean the various transitions, we will use 2 number of consecutive ones for this purpose. So, if there are 3 number of codes available, we will write C1 first, then followed by 2 consecutive ones, then followed by C2, once again followed by C2 consecutive ones, then followed by C3. So, in this way it is possible to represent any number of transitions in the binary form. So, here is the description. So, suppose if m is a transition given for you, there is a Turing machine given for us with q as a set of all states, the input alphabet is 0, 1, then we are having the tape alphabet gamma, transitions starting state is q1, then there is a final state or set of final states, then blank, that is denoting the blank position of a tape. So, with n number of transitions. So, in that case you write the code for the first transition as we have done in the previous slide. So, it is going to be C1, then you write the transition for the there is a code for the transition 2, it is going to be C2, and in between C1 and C2 we use 2 consecutive ones as the separators. So, then followed by C2, once again we write C2 consecutive ones, then C3, and finally it is going to be Cn as the last transition. So, it looks like a single binary, that is string, which is having zeros and ones, but if you read it as a number, it is possible. So, which is going to be some position in the lexicographic ordering of strings from the alphabet 0, 1. So, we will get a number as output. So, now the question is, that is after describing the Turing machine in the binary form, so how do you describe a Turing machine instance? So, every time when you are given a problem, we will be having a Turing machine plus a string, that is the input, which is to be validated by the Turing machine. So, Turing machine alone is of that is not usable in terms of problem solving. So, you say what is going to be Turing machine, then what is the input to be given for the Turing machine to see whether the input is successfully accepted by the Turing machine or not. So, now what shall we do is find out the mechanism for describing a Turing machine instance, which is nothing but a pair containing a Turing machine followed by the input. Already we have used 2 kinds of separators. One is a separator meant for that is differentiating the individual components of a transition, that is nothing but 1, and another one is the separator for separating the individual transitions of the Turing machine, that is nothing but 2 consecutive ones. So, now we need the third type of separator, which is to be used for differentiating what is a Turing machine and what is its input. The Turing machine codes are written in the form that is C1, then 2 consecutive ones, then C2, then finally it is Cn. So, now let us assume that W is the input to be processed by this particular Turing machine. Then we will use 3 consecutive ones for separating the Turing machine code from the input of the Turing machine. So, that is what here we are having. So, we have there is a Turing machine m, and then there is a number of transitions given for us. Then W is the input which is to be processed by that particular Turing machine. So, now the question is, how do you describe this entire Turing machine instance in a single binary string? So actually we have that is the pair m comma w to be coded. So m is the Turing machine and w is a string to be processed. So in this case we have 4 number of transitions. The first one is del of q1 comma 1 is q3 comma 0 comma r, then q3 comma 0 is q1 comma 1 comma r, and finally it is q3 comma blank is going to be q3 comma 1 comma l. So now we have the tape alphabet. The tape alphabet is nothing but 0, 1 and another one is called blank. So now the tape alphabet is going to be coded in terms of zeros in unary form. The states are also going to be coded in the unary form. Let us take the very first, that is transition. It starts with the state, that is q1, and the input symbol is going to be 1. So q1 is the first state. So we find that 0, there is a single 0 denotes the state, that is the source state, that is where from we will be starting the transition. Then we have the input symbol, that is 1, which is the second symbol as far as the tape alphabet is concerned. So here we have the tape alphabet 0, 1 and then B. So 0 is the first symbol, which will be 0 coded by 0 itself. Then 1 is second symbol. In the unary form 1 is coded as 2 zeros. So that is what here we are having 2 number of zeros. So now the inputs are all described already. A 0 followed by 1 as a separator, followed by 2 consecutive zeros, then followed by, now we will describe the output. So there are 3 number of output components. One is what is the resulting state, then what is going to be the resulting symbol, that is a replacement given for this input, then what is the direction in which we have to move. Since q3 is the third state, it is described by using 3 consecutive zeros. So that is a first component of the output. Then 0 is the replacement given for 1, which is nothing but the first symbol as far as the tape alphabet is concerned, that is going to be denoted by a single 0, then followed by the direction, which is going to be r. Since we are having 2 number of directions, both L and R, L is coded by using 0, I mean that is 1 number of 0, and R is coded by using 2 consecutive number of zeros. So that is what we are having 0 0. So till this we find the code for the first transition. So here we have a single 0, it means state 1, 2 symbols mean the second tape symbol, then 3 zeros as the third component, which means the resulting state is going to be third state of the set of all states, and the fourth component is single 0, which means the first tape alphabet symbol is going to be the replacement given for the input symbol, and finally the direction to be moved is the second direction, that is nothing but R. So that is what the first transition. So now we have a separator, that is 1 comma 1, so 1 followed by 1, then you write the second transition. The second transition we start with the third state of the set of all states q3, then here we have 0, then q1, 1 and R. So it means 3 zeros followed by a 1, followed by 1 0, followed by a 1, followed by 1 0, followed by a 1, followed by 2 consecutive zeros because of the replacement is the second symbol from the tape alphabet, then followed by it is going to be R, that is nothing but the direction to be moved, which is the second direction in the direction set. So if you are looking at the last one, it is going to be q3. Here we find that there are 3 number of consecutive that is zeros available, then B is going to be the third symbol in the tape alphabet, that is what 3 consecutive zeros, then q3 is the resulting state, 3 consecutive zeros, 1 is the tape symbol, and finally L is nothing but the direction 1 in the direction set. So where we have the 0 for that. So far we have seen only the representation for every transition given in the Turing machine. It means that the Turing machine is described, that is as far as this pair is concerned, M is described in the binary form. So now the question is, how do you describe this W, that is going to be the input for the tape which is to be processed, input for the Turing machine which is going to be processed. So already I said that there are 3 consecutive ones to be used as separator for separating the Turing machine code from the input for the Turing machine. So you will be writing that is 3 consecutive ones, then followed by, it is not required to bother about anything, you simply write everything available in the input. So as far as the coding of the input for the Turing machine is concerned, whatever is available in the literally, they will be completely described in the order in which it is given in the input. So there is no need of interpreting the ones and zeros as unary form. the input itself is completely described in the binary form, but whereas as far as all the remaining components, that is C1 to Cn are concerned, they are all described by the unary form except the binary form, that is your input. So, this is how we are representing the Turing machines in binary form, so that it will be very easy for us to represent or load a Turing machine into the tape of another Turing machine, so that we will be able to do many different solve many different problems. Let us go for a break. After the break, we will continue the lecture. Welcome back. We have seen that is how a Turing machine is coded using binary form. That is, in the case of conventional representation, we find difficulties in loading them into the Turing machine tape, and now it is, if it is represented in the binary form, it will be much easier for us. So, we are going to transform the Turing machine in the descriptive form into the binary form. That is what we have done. So, now using this binary representation for the Turing machine, we will be able to define different languages and their proofs for proving their class of the language, the class in which the language belongs to. The first language we have taken is the diagonal language. So, we will be calling it as diagonalization language or diagonal language. So, what it is first of all? So, let us see, that is your WI is the lexicographic ordering, that is when you are writing the lexicographic ordering from the alphabet 0, 1, that is a binary alphabet. In that, each string is going to have some index. So, if it is going to be the ith string, then the string is called Wi. I is the position of the string in the lexicographic ordering of the binary form from the alphabet 0, 1. Wi is the ith string in the lexicographic ordering, and here we give interpretation for this Wi as the ith Turing machine of the lexicographic ordering. It means this Mi is going to be Turing machine. So, this Mi is nothing but it is available in the form of a binary form. So, that binary form is the ith string in the lexicographic ordering from the alphabet 0, 1. So, there is no guarantee that this Wi is always going to be valid Turing machine. It may be valid Turing machine or it may not be. If it is a valid Turing machine, there will be valid codes available in the Turing machine, and if it is not a valid Turing machine, we will not be able to even find a single code which is going to be a valid code, single transition. So, if you find that the Turing machine which we mean by this Wi is not going to be valid Turing machine, then immediately we consider this Turing machine as a one with null language. So, we will say that it is a Turing machine, but what kind of interpretation given for the Turing machine is, it is a machine with no language. So, if Wi is not a valid Turing machine, then Mi is expected to be a Turing machine immediately halted on any input. That means, the language of the Turing machine is always empty. So, that is the case if Wi fails to be a Turing machine. But if Wi is a valid Turing machine, then we know that there will be a language available for the Turing machine. So, in that case, we will use it for the diagonal language. So, now we are going for considering the set of all strings Wi such that Wi is not in L of Mi. It means that for every that is Turing machine, so there is a language available for us, and let us see that is Wi is a Turing machine, and we take this Wi as the input for the Turing machine also. So, if Wi is not in the language of the Turing machine described by the code Wi, then we will say that this particular Turing machine is going to be in a set, and we call that set as diagonal language. So, here is the description. LD is the set of all strings such that Wi is not in L of Mi. That is, the string that is Wi itself is the description for the Turing machine or the Turing machine. If Wi is not in L of Mi, then we will call this set that is Wi as the diagonal language. Here is the table. So, we find that there are rows and columns. We have that is the Turing machine or the code that is going to be 1, 2, 3, 4 etc., and here also 1, 2, 3, 4 etc. So, the presence of a 0 or 1 inside the table denotes that, suppose if it is going to be I comma jth cell, it means that the ith Turing machine accepts the jth input. The presence of a 0 denotes that the ith Turing machine does not accept the jth string. So, 1 does not accept 4 means 0. If 1 accepts 3, then it is going to be 1. So, these values are sample values. So, these positions, that is 1, 2, 3, 4 all are denoting that W1, W2, W3 etc. up to infinite, it goes in an infinite manner. So, now look at the diagonal values. Here we find that that is 0, which is nothing but 1 comma 1. It means, so this Wi is not going to be accepted by the Turing machine Mi, that is W1 is not accepted by M1. Then 2, it means W2 is accepted by M2, then W3 is accepted by M3, then W4 is accepted by M4, and finally in this table W5 is not accepted by M5. So, every row is called the characteristic vector of the ith Turing machine. So, if you take the ith row available in your table, we will be having a sequence of zeros and ones, and if you collect exactly only that row, we can call it as the characteristic vector for the ith Turing machine. So, now it is possible to form a characteristic vector from the main diagonal of this table. Before going for obtaining the characteristic vector from the main diagonal of the table, we will go for finding the complement of that. So, complement every value available in the main diagonal, then form the characteristic vector. As such, what this table says is, if a presence of 1 is there in Wi comma Mi, it means that this Mi is accepted by Wi. But once complemented, we know that the zeros will become 1 and 1s will become 0. So, if it is going to be replaced by 1, we will say that this W1 is not accepted by M1. The presence of 1 says W1 is not accepted by this, and here once it is complemented, this will become a 0. It means that this W2 accepts M2 or accepted by M2. Here is the table available. So, after complementing, we find that 1 is available here, and finally here it is 5 comma 5 is also 1. So, when you take the characteristic vector from this language, we know that the first entry is 1, the second entry is 0, third entry is 0, fourth entry is 0, and the fifth entry is once again 1. So, it means in the characteristic vector for this diagonal language, we will be having the string called W1 and we will be having the string called W5. Only those two are the strings available in the characteristic vector for this particular table. It means in the diagonal language, we are having the string W1 and only W5. So, W2, W3 and W4, they are all not included in the characteristic vector for the diagonal language, which means those are the strings not available in the language. So, when you look at the description, so we find the ith row is the characteristic vector for the Turing machine Mi. The diagonal values are telling that whether Mi accepts Wi or not, and when you are complementing all the values in the diagonal, we will be getting a characteristic vector. So, now the diagonal elements is actually used for forming the characteristic vector for LD. So, LD can be described by collecting the characteristic vector from the table. So, now the question is what kind of language it is. So, LD is going to be there is a language which contains some number of strings, and we know that each and every string is going to be a valid Turing machine with either the language is empty or the language is non-empty. So, now the question is what kind of language this is being called. It is going to be the diagonal language, but what class it belongs to. So, this diagonal language belongs to the non-recursively enumerable language. It means it is certainly not possible to find out one Turing machine capable of accepting the entire collection of strings available in the diagonal language. So, that is the meaning of saying that this belongs to the non-recursively enumerable language. So, here is the proof available for us. So, the first point here is, suppose if we find that LD, that is your diagonal language, is going to be your L of m. That means there exists a Turing machine m whose language is LD. LD is going to be recursively enumerable language. Certainly there exists a Turing machine. So it is going to be proof by contradiction. So if LD is going to be a recursively enumerable language with a Turing machine called m, then there is a code for that m, let it be mi, that is ith Turing machine. So now you take that is your wi, a string. If wi is in LD, then mi should accept wi. The meaning is, if wi is a string which is there in LD, then mi should accept wi. But what the definition of LD says is, wi is not in LD. That is, by the definition of the wi or the definition of the diagonal language, we have to say that wi is not in LD. The second point to be mentioned here is, so wi either may be in the language that is LD or it may not be in the language called LD. If wi is not in LD, then it does not accept the rest wi. That is the meaning of this. If wi is not in LD, then the Turing machine mi, which is an assumed Turing machine, it should not accept wi. But by the definition of LD, we know that if mi does not accept wi, then wi is in LD. So we have two cases. What will happen suppose wi is in LD, and what will happen if wi is not in LD. If wi is in LD, then we finally conclude that wi is not in LD, which is a contradiction, and if wi is not in LD, then we get a conclusion that is wi is in LD. So what it shows is, wi can neither be in LD nor fail to be in LD. So we find that is, we are not able to prove that wi is in LD, and we are not able to prove that wi is not in that is LD. So which is going to be the contradiction, which gives us a proof that the language LD has no Turing machine for its recognition. If a language has no Turing machine for its recognition, then immediately we can say that it is going to be the class of language called non-recursively enumerable language. So this is the first language we see as a non-recursively enumerable language. To summarize, we have seen the coding for that is Turing machines, that is how the individual Turing machines are represented in the binary form. Then we have seen the diagonal language definition, and also we have seen the proof for that is how the diagonal language is going to be proved as non-recursively enumerable language. It means that it is a language for which there is no Turing machine at all available. So the questions here, the representation, that is what is the advantage in representing the Turing machine using integer codes. It is just because of, if you want to load a Turing machine as input for another Turing machine, it is required to have the Turing machine in the form of some binary. It will be very easy for representation. Then maybe the there is given a Turing machine, how it will be transformed into the binary form. Then what is the definition for diagonal language, and how do we prove this diagonal language as a non-recursively enumerable language. These are all the question components as far as this particular episode is concerned. So with this I conclude this episode. Thank you all.